Welcome to the Explainer. Today we're going to crack open a device you probably see all the time, but it's hiding this surprisingly complex little engine right inside. I'm talking about the electric bell.
Okay, just a quick heads up before we jump in. This is the advanced explainer. So if you're just getting your feet wet with electromagnetism, you might want to check out our introductory explainer first. We posted that a few days ago. But for everyone else, all right, let's get into it. So here's the real puzzle, right? The thing that makes the electric bells so fascinating. How does one single static press of a button create this continuous rapid-fire ring? That's the elegant complexity we are going to unpack today. All right, here's how we're going to break it down. We'll start with the electromagnetic heart of the device. Then we're going to dissect that really ingenious make and break cycle. After that, we'll take a quick look at its history, and then we'll wrap it all up by summarizing the core science. Okay, let's dive into our first section. See, at the absolute core of the bell is this really remarkable piece of physics, its electromagnetic heart.
So, these are the main players in our story. You've got your electromagnet, the armature, the hammer, the gong, the whole crew. And every single part has a super crucial role in what's basically a perfectly timed electromechanical dance. We're about to see exactly why those choices of material and even shape are so critical.
Now, the real hero of our story has got to be the electromagnet. See, unlike a regular permanent magnet, its power is totally controllable. It only even exists when an electric current is flowing through its coils. And that one feature, that's the key to this whole thing.
Right, so this is the crucial difference. It's all about being able to switch the magnetism on and off. I mean, think about it. A permanent magnet would pull the hammer, it would strike the bell once, and then it would just get stuck there. Game over. It's the electromagnet's ability to just turn off that lets the whole system reset and go again and again and again. And the strength of this magnet isn't just random. Thanks to Ampere's law, we know it's directly tied to two things we can control: how much current we push through it and how many times we wrap that wire around the core. This is huge because it lets engineers design a magnet with the exact right amount of pull, the perfect magnetic flux, for whatever job it needs to do.
Okay, so we've got our controllable magnet. Now, let's see how that powers the bell's most brilliant feature, the self-interrupting circuit. Honestly, this is where the real magic happens.
And this whole 6-step dance, it happens dozens of times every single second. It is a perfect tiny feedback loop where the bell is literally turning itself on and off over and over again. And that's what creates that continuous ring from just one press of the button. What's so cool about this idea is just how self-perpetuating the whole thing is. The bell's own movement is what regulates its own power. It's this beautiful little example of electromechanical automation, and it just keeps going and going as long as you're holding that switch down. So, let's walk through it. It all kicks off the second you press that button, which closes the circuit. Instantly, electrical energy zaps into the coil. And that U-shape of the core, that's not an accident. It's brilliant. It concentrates the magnetic field right between its two poles, which creates a really strong focused pull. And just like that, magnetic energy turns into motion, kinetic energy, and yanks that armature right across the gap.
Okay, this is the most clever part of the entire setup. The very action of ringing the bell is also the action that cuts its own power. See that little contact screw the armature was touching? That thing acts like a tiny automatic kill switch. The instant the hammer hits the gong, the circuit breaks. It's just genius.
And here's the thing. The super fast reset is only possible because the armature is made of a specific material, soft iron. Now, soft iron has what we call low magnetic retentivity. What that means is it gets really magnetic when the power's on, but it loses that magnetism almost instantly when you cut the current. If you tried to use hard iron, well, it would become a permanent magnet and just stay stuck. Total failure. But with soft iron, the magnet just disappears. The spring takes over, snaps the armature back to the contact screw, and boom, the whole cycle starts all over again.
All right, moving on. This super ingenious mechanism wasn't just for doorbells, Its core principles were so solid, so robust, that they evolved and got adapted for all sorts of critical technologies.
And this didn't happen overnight. It was a really gradual process of refining an idea over decades. It all started with William Sturgeon inventing the electromagnet. Then folks like James Marsh experimented with it. And eventually, innovators like John Muir are the ones who really perfected it, turning what was basically a telegraph sounder into the bell that we all recognize today. And what's really cool is that by just tweaking the basic design, engineers created a whole family of different devices. For example, if you get rid of that self-interrupting contact screw, you get a single-stroke bell, perfect for tapping out coded signals on railways. Or take away the gong, and now you've got a quiet buzzer, for timers or desktop alerts. Same principle, different job. Now, of course, today most of this has been replaced by solid-state electronics. We use things called piezoelectric transducers. They basically vibrate crystals to make sound. But even though we've moved on, the pure cleverness of the original electromechanical design, with its perfect little feedback loop and really smart use of materials, it really is a masterclass in engineering.
All right, so to wrap this all up, let's boil everything we've talked about down to the 5 core scientific principles that make the electric bell actually work. So there you have it, these 5 principles. Everything from the basic physics of controllable magnetism all the way to the beautiful logic of that self-interrupting feedback loop, they all come together to create a system that looks simple on the outside but is just deeply elegant in how it operates. It's like a perfect little symphony of physics happening inside a tiny box. And that leaves us with a final thought. The electric bell is just such a great reminder that truly elegant engineering is often hiding in plain sight. So it makes you wonder, right? What other simple, everyday devices out there are powered by such clever and complex feedback loops?